is a nearly perfect sphere of hot plasma, with internal convective motion that generates a magnetic field via a dynamo process. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometers, 864,000 miles, or 109 times that of Earth, and its mass is about 330,000 times that of Earth. It accounts for about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, 73%, the rest is mostly helium, 25%, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star, G2V, based on its spectral class. As such, it is informally and not completely accurately referred to as a yellow dwarf. Its light is closer to white than yellow. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun currently fuses about 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. This energy, which can take between 10,000 and 170,000 years to escape from its core, is the source of the Sun's light and heat. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature while its outer layers expand, eventually transforming the Sun into a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus, and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers and become a dense type of cooling star known as a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognized since prehistoric times, and the Sun has been regarded by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of solar calendars, one of which is the predominant calendar in use today. Name and etymology. The English proper name Sun developed from Old English sun and may be related to south. Cognates to English sun appear in other Germanic languages, including Old Frisian sun, son, Old Saxon sunna, Middle Dutch son, Modern Dutch zon, Old High German sunna, Modern German son, Old Norse sunna, and Gothic sunno. All Germanic terms for the sun stem from Proto-Germanic sunnon. The Latin name for the Sun, Sol, is not commonly used in everyday English. Sol is also used by planetary astronomers to refer to the duration of a solar day on another planet, such as Mars. The related word solar is the usual adjectival term used, in terms such as solar day, solar eclipse, and solar system. The English weekday name Sunday stems from Old English, sun and dag, sun's day, from before 700, and is ultimately a result of a Germanic interpretation of Latin dies solis, itself a translation of the Greek mu rho alpha lambda omicron upsilon, hemera helio. General characteristics. The Sun is a G-type main sequence star that comprises about 99.86% of the mass of the solar system. The Sun has an absolute magnitude of plus 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. The Sun is a population I, or heavy element rich, star. The formation of the Sun may have been triggered by shock waves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, relative to the abundances of these elements in so-called population II, heavy element poor, stars. The heavy elements could most plausibly have been produced by endothermic nuclear reactions during a supernova, or by transmutation through neutron absorption within a massive second-generation star. The Sun is by far the brightest object in the Earth's sky, with an apparent magnitude of -26.74. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of -1.46. The mean distance of the Sun's center to Earth's center is approximately 1 astronomical unit, about 150 million kilometers, 93 million miles, though the distance varies as Earth moves from perihelion in January to aphelion in July. At this average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 19 seconds, while light from the closest points of the Sun and Earth takes about 2 seconds less. The energy of this sunlight supports almost all life on Earth by photosynthesis, and drives Earth's climate and weather. The Sun does not have a definite boundary, but its density decreases exponentially with increasing height above the photosphere. For the purpose of measurement, however, the Sun's radius is considered to be the distance from its center to the edge of the photosphere, the apparent visible surface of the Sun. By this measure, the Sun is a near-perfect sphere with an oblateness estimated at about 9 millionths, which means that its polar diameter differs from its equatorial diameter by only 10 kilometers, 6.2 miles. The tidal effect of the planets is weak and does not significantly affect the shape of the Sun. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport in the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. Viewed from Earth as it orbits the Sun, the apparent rotational period of the Sun at its equator is about 28 days. Sunlight. The solar constant is the amount of power that the Sun deposits per unit area that is directly exposed to sunlight. The solar constant is equal to approximately 1368 W/m2, watts per square meter, at a distance of 1 astronomical unit, AU, from the Sun, that is, on or near Earth. Sunlight on the surface of Earth is attenuated by Earth's atmosphere, so that less power arrives at the surface, closer to 1000 W/m2, in clear conditions when the Sun is near the zenith. Sunlight at the top of Earth's atmosphere is composed, by total energy, of about 50% infrared light, 40% visible light, and 10% ultraviolet light. The atmosphere in particular filters out over 70% of solar ultraviolet, especially at the shorter wavelengths. Solar ultraviolet radiation ionizes Earth's day-side upper atmosphere, creating the electrically conducting ionosphere. The Sun's color is white, with a C-color space index near 0.3 when viewed from space or when the Sun is high in the sky. When measuring all the photons emitted, the Sun is actually emitting more photons in the green portion of the spectrum than any other. When the Sun is low in the sky, atmospheric scattering renders the Sun yellow, red, orange, or magenta. Despite its typical whiteness, most people mentally picture the Sun as yellow. The reasons for this are the subject of debate. The Sun is a G2V star, with G2 indicating its surface temperature of approximately 5778 K, 5505 degrees Celsius, 9941 degrees Fahrenheit, and V that it, like most stars, is a main sequence star. The average luminance of the Sun is about 1.88 gigacandela per square meter, but as viewed through Earth's atmosphere, this is lowered to about 1.44 GCD/m2. However, the luminance is not constant across the disk of the Sun, limb darkening. Composition. The Sun is composed primarily of the chemical elements hydrogen and helium. At this time in the Sun's life, they account for 74.9% and 23.8% of the mass of the Sun in the photosphere, respectively. All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen, roughly 1% of the Sun's mass, carbon, 0.3%, neon, 0.2%, and iron, 0.2%, being the most abundant. The Sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally it would have contained about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. The hydrogen and most of the helium in the Sun would have been produced by Big Bang nucleosynthesis in the first 20 minutes of the universe, and the heavier elements were produced by previous generations of stars before the Sun was formed, and spread into the interstellar medium during the final stages of stellar life and by events such as supernovae. Since the Sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the Sun has gradually changed. Within the core, the proportion of helium has increased from about 24% to about 60% due to fusion, and some of the helium and heavy elements have settled from the photosphere towards the center of the Sun because of gravity. The proportions of metals, heavier elements, is unchanged. Heat is transferred outward from the Sun's core by radiation rather than by convection, see radiative zone below, so the fusion products are not lifted outward by heat, they remain in the core and gradually an inner core of helium has begun to form that cannot be fused because presently the Sun's core is not hot or dense enough to fuse helium. In the current photosphere the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostar phase, before nuclear fusion in the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years this gradual buildup will eventually cause the Sun to exit the main sequence and become a red giant. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. The solar heavy element abundances described above are typically measured both using spectroscopy of the Sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostar Sun and are thus not affected by settling of heavy elements. The two methods generally agree well. Singly ionized iron group elements. In the 1970s, much research focused on the abundances of iron group elements in the Sun. Although significant research was done, until 1978 it was difficult to determine the abundances of some iron group elements, for example cobalt and manganese, via spectrography because of their hyperfine structures. The first largely complete set of oscillator strengths of singly ionized iron group elements were made available in the 1960s, and these were subsequently improved. In 1978, the abundances of singly ionized elements of the iron group were derived. Isotopic composition. Various authors have considered the existence of a gradient in the isotopic compositions of solar and planetary noble gases, for example correlations between isotopic compositions of neon and xenon in the Sun and on the planets. Prior to 1983, it was thought that the whole Sun has the same composition as the solar atmosphere. In 1983, it was claimed that it was fractionation in the Sun itself that caused the isotopic composition relationship between the planetary and solar wind implanted noble gases. Structure and fusion. The structure of the Sun contains the following layers. Core, the innermost 20 to 25% of the Sun's radius, where temperature, energies, and pressure are sufficient for nuclear fusion to occur. Hydrogen fuses into helium, which cannot currently be fused at this point in the Sun's life. The fusion process releases energy, and the helium gradually accumulates to form an inner core of helium within the core itself. Radiative zone, convection cannot occur until much nearer the surface of the Sun. Therefore, between about 20 to 25% of the radius, and 70% of the radius, there is a radiative zone in which energy transfer occurs by means of radiation, photons, rather than by convection. Tachocline, the boundary region between the radiative and convective zones. Convective zone, between about 70% of the Sun's radius and a point close to the visible surface, the Sun is cool and diffuse enough for convection to occur, and this becomes the primary means of outward heat transfer, similar to weather cells which form in the Earth's atmosphere. Photosphere, the deepest part of the Sun which we can directly observe with visible light. Because the Sun is a gaseous object, it does not have a clearly defined surface, its visible parts are usually divided into a photosphere and atmosphere. Atmosphere, a gaseous halo surrounding the Sun, comprising the chromosphere, solar transition region, corona and heliosphere. These can be seen when the main part of the Sun is hidden, for example, during a solar eclipse. Core. The core of the Sun extends from the center to about 20 to 25% of the solar radius. It has a density of up to 150 grams/cm3, about 150 times the density of water, and a temperature of close to 15.7 million kelvins, K. By contrast, the Sun's surface temperature is approximately 5,800 K. Recent analysis of SOHO mission data favors a faster rotation rate in the core than in the radiative zone above. Through most of the Sun's life, energy has been produced by nuclear fusion in the core region through a series of nuclear reactions called the PP, proton-proton, chain. This process converts hydrogen into helium. Only 0.8% of the energy generated in the Sun comes from another sequence of fusion reactions called the CNO cycle, though this proportion is expected to increase as the Sun becomes older. The core is the only region in the Sun that produces an appreciable amount of thermal energy through fusion. 99% of the power is generated within 24% of the Sun's radius, and by 30% of the radius, fusion has stopped nearly entirely. The remainder of the Sun is heated by this energy as it is transferred outwards through many successive layers, finally to the solar photosphere where it escapes into space through radiation, photons, or advection, massive particles. The proton-proton chain occurs around 9.2 times 1037 times each second in the core, converting about 3.7 times 1038 protons into alpha particles, helium nuclei, every second, out of a total of 8.9 times 1056 free protons in the Sun, or about 6.2 times 1011 kilograms/s. Fusing 4 free protons, hydrogen nuclei, into a single alpha particle, helium nucleus, releases around 0.7% of the fused mass as energy, so the Sun releases energy at the mass-energy conversion rate of 4.26 million metric tons per second, which requires 600 metric megatons of hydrogen, for 384.6 yottawatts, 3.846 times 1026 W, or 9.192 times 1010 megatons of TNT per second. However, the large power output of the Sun is mainly due to the huge size and density of its core, compared to Earth and objects on Earth, with only a fairly small amount of power being generated per cubic meter. Theoretical models of the Sun's interior indicate a maximum power density, or energy production, of approximately 276.5 watts per cubic meter at the center of the core, which is about the same rate of power production as takes place in reptile metabolism or a compost pile. The fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers, reducing the density and hence the fusion rate and correcting the perturbation, and a slightly lower rate would cause the core to cool and shrink slightly, increasing the density and increasing the fusion rate and again reverting it to its present rate. Radiative zone. From the core out to about 0.7 solar radii, thermal radiation is the primary means of energy transfer. The temperature drops from approximately 7 million to 2 million kelvins with increasing distance from the core. This temperature gradient is less than the value of the adiabatic collapse rate and hence cannot drive convection, which explains why the transfer of energy through this zone is by radiation instead of thermal convection. Ions of hydrogen and helium emit photons, which travel only a brief distance before being reabsorbed by other ions. The density drops 100-fold, from 20 grams/cm3 to 0.2 grams/cm3. From 0.25 solar radii to the 0.7 radii, the top of the radiative zone. Tachocline. The radiative zone and the convective zone are separated by a transition layer, the tachocline. This is a region where the sharp regime change between the uniform rotation of the radiative zone and the differential rotation of the convection zone results in a large shear between the two, a condition where successive horizontal layers slide past one another. Presently, it is hypothesized, see solar dynamo, that a magnetic dynamo within this layer generates the Sun's magnetic field. Convective zone. The Sun's convection zone extends from 0.7 solar radii, 500,000 kilometers, to near the surface. In this layer, the solar plasma is not dense enough or hot enough to transfer the heat energy of the interior outward via radiation. Instead, the density of the plasma is low enough to allow convective currents to develop and move the sun's energy outward towards its surface. Material heated at the tachocline picks up heat and expands, thereby reducing its density and allowing it to rise. As a result, an orderly motion of the mass develops into thermal cells that carry the majority of the heat outward to the sun's photosphere above. Once the material diffusively and radiatively cools just beneath the photospheric surface, its density increases, and it sinks to the base of the convection zone, where it again picks up heat from the top of the radiative zone and the convective cycle continues. At the photosphere, the temperature has dropped to 5,700 K and the density to only 0.2 grams/m3, about 1/6000th the density of air at sea level. The thermal columns of the convection zone form an imprint on the surface of the sun, giving it a granular appearance called the solar granulation at the smallest scale and supergranulation at larger scales. Turbulent convection in this outer part of the solar interior sustains small-scale dynamo action over the near-surface volume of the sun. The sun's thermal columns are Bénard cells and take the shape of hexagonal prisms. Photosphere. The visible surface of the sun, the photosphere, is the layer below which the sun becomes opaque to visible light. Photons produced in this layer escape the sun through the transparent solar atmosphere above it and become solar radiation, sunlight. The change in opacity is due to the decreasing amount of H- ions, which absorb visible light easily. Conversely, the visible light we see is produced as electrons react with hydrogen atoms to produce H- ions. The photosphere is tens to hundreds of kilometers thick, and is slightly less opaque than air on Earth. Because the upper part of the photosphere is cooler than the lower part, an image of the sun appears brighter in the center than on the edge or limb of the solar disk, in a phenomenon known as limb darkening. The spectrum of sunlight has approximately the spectrum of a black body radiating at 5,777 K, interspersed with atomic absorption lines from the tenuous layers above the photosphere. The photosphere has a particle density of 1023 meters-3, about 0.37% of the particle number per volume of Earth's atmosphere at sea level. The photosphere is not fully ionized. The extent of ionization is about 3%, leaving almost all of the hydrogen in atomic form. During early studies of the optical spectrum of the photosphere, some absorption lines were found that did not correspond to any chemical elements then known on Earth. In 1868, Norman Lockyer hypothesized that these absorption lines were caused by a new element that he dubbed helium, after the Greek sun god Helios. 25 years later, helium was isolated on Earth. Atmosphere. During a total solar eclipse, when the disk of the sun is covered by that of the moon, parts of the sun's surrounding atmosphere can be seen. It is composed of four distinct parts: the chromosphere, the transition region, the corona and the heliosphere. The coolest layer of the sun is a temperature minimum region extending to about 500 kilometers above the photosphere, and has a temperature of about 4,100 K. This part of the sun is cool enough to allow the existence of simple molecules such as carbon monoxide and water, which can be detected via their absorption spectra. The chromosphere, transition region, and corona are much hotter than the surface of the sun. The reason is not well understood, but evidence suggests that all vane waves may have enough energy to heat the corona. Above the temperature minimum layer is a layer about 2,000 kilometers thick, dominated by a spectrum of emission and absorption lines. It is called the chromosphere from the Greek root chroma, meaning color, because the chromosphere is visible as a colored flash at the beginning and end of total solar eclipses. The temperature of the chromosphere increases gradually with altitude, ranging up to around 20,000 K near the top. In the upper part of the chromosphere, helium becomes partially ionized. Above the chromosphere, in a thin, about 200 kilometers, transition region, the temperature rises rapidly from around 20,000 K in the upper chromosphere to coronal temperatures closer to 1 million K. The temperature increase is facilitated by the full ionization of helium in the transition region, which significantly reduces radiative cooling of the plasma. The transition region does not occur at a well-defined altitude. Rather, it forms a kind of nimbus around chromospheric features such as spicules and filaments, and is in constant, chaotic motion. The transition region is not easily visible from Earth's surface, but is readily observable from space by instruments sensitive to the extreme ultraviolet portion of the spectrum. The corona is the next layer of the Sun. The low corona, near the surface of the Sun, has a particle density around 1015 meters-3 to 1016 meters-3. The average temperature of the corona and solar wind is about 1 million to 2 million K, however, in the hottest regions it is 8 million to 20 million K. Although no complete theory yet exists to account for the temperature of the corona, at least some of its heat is known to be from magnetic reconnection. The corona is the extended atmosphere of the Sun, which has a volume much larger than the volume enclosed by the Sun's photosphere. A flow of plasma outward from the Sun into interplanetary space is the solar wind. The heliosphere, the tenuous outermost atmosphere of the Sun, is filled with the solar wind plasma. This outermost layer of the Sun is defined to begin at the distance where the flow of the solar wind becomes supervolcanic, that is, where the flow becomes faster than the speed of all vane waves, at approximately 20 solar radii, 0.1 astronomical units. Turbulence and dynamic forces in the heliosphere cannot affect the shape of the solar corona within, because the information can only travel at the speed of all vane waves. The solar wind travels outward continuously through the heliosphere, forming the solar magnetic field into a spiral shape, until it impacts the heliopause more than 50 astronomical units from the Sun. In December 2004, the Voyager 1 probe passed through a shock front that is thought to be part of the heliopause. In late 2012, Voyager 1 recorded a marked increase in cosmic ray collisions and a sharp drop in lower energy particles from the solar wind, which suggested that the probe had passed through the heliopause and entered the interstellar medium. Photons and neutrinos. High-energy gamma-ray photons initially released with fusion reactions in the core are almost immediately absorbed by the solar plasma of the radiative zone, usually after traveling only a few millimeters. Re-emission happens in a random direction and usually at a slightly lower energy. With this sequence of emissions and absorptions, it takes a long time for radiation to reach the Sun's surface. Estimates of the photon travel time range between 10,000 and 170,000 years. In contrast, it takes only 2.3 seconds for the neutrinos, which account for about 2% of the total energy production of the Sun, to reach the surface. Because energy transport in the Sun is a process that involves photons in thermodynamic equilibrium with matter, the timescale of energy transport in the Sun is longer, on the order of 30 million years. This is the time it would take the Sun to return to a stable state, if the rate of energy generation in its core were suddenly changed. Neutrinos are also released by the fusion reactions in the core, but, unlike photons, they rarely interact with matter, so almost all are able to escape the Sun immediately. For many years, measurements of the number of neutrinos produced in the Sun were lower than theories predicted by a factor of 3. This discrepancy was resolved in 2001 through the discovery of the effects of neutrino oscillation. The Sun emits the number of neutrinos predicted by the theory, but neutrino detectors were missing 2/3 of them because the neutrinos had changed flavor by the time they were detected. Magnetic activity. Magnetic field. The Sun has a magnetic field that varies across the surface of the Sun. Its polar field is 1 to 2 Gauss, 0.00001 to 0.0002 T, whereas the field is typically 3000 Gauss, 0.3 T, in features on the Sun called sunspots, and 10 to 100 Gauss, 0.001 to 0.01 T, in solar prominences. The magnetic field also varies in time and location. The quasi-periodic 11-year solar cycle is the most prominent variation, in which the number and size of sunspots waxes and wanes. Sunspots are visible as dark patches on the Sun's photosphere, and correspond to concentrations of magnetic field where the convective transport of heat is inhibited from the solar interior to the surface. As a result, sunspots are slightly cooler than the surrounding photosphere, and, so, they appear dark. At a typical solar minimum, few sunspots are visible, and occasionally none can be seen at all. Those that do appear are at high solar latitudes. As the solar cycle progresses towards its maximum, sunspots tend to form closer to the solar equator, a phenomenon known as Sporer's law. The largest sunspots can be tens of thousands of kilometers across. An 11-year sunspot cycle is half of a 22-year Babcock-Leeton dynamo cycle, which corresponds to an oscillatory exchange of energy between toroidal and poloidal solar magnetic fields. At solar cycle maximum, the external poloidal dipolar magnetic field is near its dynamo cycle minimum strength, but an internal toroidal quadrupolar field, generated through differential rotation within the tachocline, is near its maximum strength. At this point in the dynamo cycle, buoyant upwelling within the convective zone forces emergence of toroidal magnetic field through the photosphere, giving rise to pairs of sunspots, roughly aligned east-west and having footprints with opposite magnetic polarities. The magnetic polarity of sunspot pairs alternates every solar cycle, a phenomenon known as the Hale cycle. During the solar cycle's declining phase, energy shifts from the internal toroidal magnetic field to the external poloidal field, and sunspots diminish in number and size. At solar cycle minimum, the toroidal field is, correspondingly, at minimum strength, sunspots are relatively rare, and the poloidal field is at its maximum strength. With the rise of the next 11-year sunspot cycle, differential rotation shifts magnetic energy back from the poloidal to the toroidal field, but with a polarity that is opposite to the previous cycle. The process carries on continuously, and in an idealized, simplified scenario, each 11-year sunspot cycle corresponds to a change, then, in the overall polarity of the Sun's large-scale magnetic field. The solar magnetic field extends well beyond the Sun itself. The electrically conducting solar wind plasma carries the Sun's magnetic field into space, forming what is called the interplanetary magnetic field. In an approximation known as ideal magnetohydrodynamics, plasma particles only move along the magnetic field lines. As a result, the outward flowing solar wind stretches the interplanetary magnetic field outward, forcing it into a roughly radial structure. For a simple dipolar solar magnetic field, with opposite hemispherical polarities on either side of the solar magnetic equator, a thin current sheet is formed in the solar wind. At great distances, the rotation of the Sun twists the dipolar magnetic field and corresponding current sheet into an Archimedean spiral structure called the Parker spiral. The interplanetary magnetic field is much stronger than the dipole component of the solar magnetic field. The Sun's dipole magnetic field of 50 to 400 μt, at the photosphere, reduces with the inverse cube of the distance to about 0.1 nt at the distance of Earth. However, according to spacecraft observations, the interplanetary field at Earth's location is around 5 nt, about 100 times greater. The difference is due to magnetic fields generated by electrical currents in the plasma surrounding the Sun. Variation in activity. The Sun's magnetic field leads to many effects that are collectively called solar activity. Solar flares and coronal mass ejections tend to occur at sunspot groups. Slowly changing high-speed streams of solar wind are emitted from coronal holes at the photospheric surface. Both coronal mass ejections and high-speed streams of solar wind carry plasma and interplanetary magnetic field outward into the solar system. The effects of solar activity on Earth include auroras at moderate to high latitudes and the disruption of radio communications and electric power. Solar activity is thought to have played a large role in the formation and evolution of the solar system. With solar cycle modulation of sunspot number comes a corresponding modulation of space weather conditions, including those surrounding Earth where technological systems can be affected. Long-term change. Long-term secular change in sunspot number is thought, by some scientists, to be correlated with long-term change in solar irradiance, which, in turn, might influence Earth's long-term climate. For example, in the 17th century, the solar cycle appeared to have stopped entirely for several decades, Few sunspots were observed during a period known as the Maunder Minimum. This coincided in time with the era of the Little Ice Age, when Europe experienced unusually cold temperatures. Earlier extended minima have been discovered through analysis of tree rings and appear to have coincided with lower than average global temperatures. A recent theory claims that there are magnetic instabilities in the core of the Sun that cause fluctuations with periods of either 41,000 or 100,000 years. These could provide a better explanation of the ice ages than the Milankovitch cycles. Life phases. The Sun today is roughly halfway through the most stable part of its life. It has not changed dramatically for over 4 billion years, and will remain fairly stable for more than 5 billion more. However, after hydrogen fusion in its core has stopped, the Sun will undergo dramatic changes, both internally and externally. Formation. The Sun formed about 4.6 billion years ago from the collapse of part of a giant molecular cloud that consisted mostly of hydrogen and helium and that probably gave birth to many other stars. This age is estimated using computer models of stellar evolution and through nucleocosmic chronology. The result is consistent with the radiometric date of the oldest solar system material, at 4.567 billion years ago. Studies of ancient meteorites reveal traces of stable daughter nuclei of short-lived isotopes, such as iron-60, that form only in exploding, short-lived stars. This indicates that one or more supernovae must have occurred near the location where the Sun formed. A shock wave from a nearby supernova would have triggered the formation of the Sun by compressing the matter within the molecular cloud and causing certain regions to collapse under their own gravity. As one fragment of the cloud collapsed, it also began to rotate because of conservation of angular momentum and heat up with the increasing pressure. Much of the mass became concentrated in the center, whereas the rest flattened out into a disk that would become the planets and other solar system bodies. Gravity and pressure within the core of the cloud generated a lot of heat as it accreted more matter from the surrounding disk, eventually triggering nuclear fusion. HD 162,826 and HD 186,302 are hypothesized stellar siblings of the Sun, having formed in the same molecular cloud. Main sequence. The Sun is about halfway through its main sequence stage, during which nuclear fusion reactions in its core fuse hydrogen into helium. Each second, more than 4 million tons of matter are converted into energy within the Sun's core, producing neutrinos and solar radiation. At this rate, the Sun has so far converted around 100 times the mass of Earth into energy, about 0.03% of the total mass of the Sun. The Sun will spend a total of approximately 10 billion years as a main sequence star. The Sun is gradually becoming hotter during its time on the main sequence, because the helium atoms in the core occupy less volume than the hydrogen atoms that were fused. The core is therefore shrinking, allowing the outer layers of the Sun to move closer to the center and experience a stronger gravitational force, according to the inverse square law. This stronger force increases the pressure on the core, which is resisted by a gradual increase in the rate at which fusion occurs. This process speeds up as the core gradually becomes denser. It is estimated that the Sun has become 30% brighter in the last 4.5 billion years. At present, it is increasing in brightness by about 1% every 100 million years. After core hydrogen exhaustion, the Sun does not have enough mass to explode as a supernova. Instead, it will exit the main sequence in approximately 5 billion years and start to turn into a red giant. As a red giant, the Sun will grow so large that it will engulf Mercury, Venus, and probably Earth. Even before it becomes a red giant, the luminosity of the Sun will have nearly doubled, and Earth will receive as much sunlight as Venus receives today. Once the core hydrogen is exhausted in 5.4 billion years, the Sun will expand into a subgiant phase and slowly double in size over about 500 million years. It will then expand more rapidly over about 500 million years until it is over 200 times larger than today and a couple of thousand times more luminous. This then starts the red giant branch phase where the Sun will spend around 1 billion years and lose around a third of its mass. After the red giant branch, the Sun has approximately 120 million years of active life left, but much happens. First, the core, full of degenerate helium ignites violently in the helium flash, where it is estimated that 6% of the core, itself 40% of the Sun's mass, will be converted into carbon within a matter of minutes through the triple alpha process. The Sun then shrinks to around 10 times its current size and 50 times the luminosity, with a temperature a little lower than today. It will then have reached the red clump or horizontal branch, but a star of the Sun's mass does not evolve blueward along the horizontal branch. Instead, it just becomes moderately larger and more luminous over about 100 million years as it continues to react helium in the core. When the helium is exhausted, the Sun will repeat the expansion it followed when the hydrogen in the core was exhausted, except that this time it all happens faster, and the Sun becomes larger and more luminous. This is the asymptotic giant branch phase, and the Sun is alternately reacting hydrogen in a shell or helium in a deeper shell. After about 20 million years on the early asymptotic giant branch, the Sun becomes increasingly unstable, with rapid mass loss and thermal pulses that increase the size and luminosity for a few hundred years every 100,000 years or so. The thermal pulses become larger each time, with the later pulses pushing the luminosity to as much as 5,000 times the current level and the radius to over 1 astronomical unit. According to a 2008 model, Earth's orbit is shrinking due to tidal forces, and, eventually, drag from the lower chromosphere, so that it will be engulfed by the Sun near the tip of the red giant branch phase, 3.8 and 1 million years after Mercury and Venus have respectively suffered the same fate. Models vary depending on the rate and timing of mass loss. Models that have higher mass loss on the red giant branch produce smaller, less luminous stars at the tip of the asymptotic giant branch, perhaps only 2,000 times the luminosity and less than 200 times the radius. For the Sun, 4 thermal pulses are predicted before it completely loses its outer envelope and starts to make a planetary nebula. By the end of that phase, lasting approximately 500,000 years, the Sun will only have about half of its current mass. The post-asymptotic giant branch evolution is even faster. The luminosity stays approximately constant as the temperature increases, with the ejected half of the Sun's mass becoming ionized into a planetary nebula as the exposed core reaches 30,000 K. The final naked core, a white dwarf, will have a temperature of over 100,000 K, and contain an estimated 54.05% of the Sun's present-day mass. The planetary nebula will disperse in about 10,000 years, but the white dwarf will survive for trillions of years before fading to a hypothetical black dwarf. Orbit and location. The Sun lies close to the inner rim of the Milky Way's Orion Arm, in the local interstellar cloud or the Gold Belt, at a distance of 7.5 to 8.5 kpc, 25,000 to 28,000 light-years, from the galactic center. The Sun is contained within the local bubble, a space of rarefied hot gas, possibly produced by the supernova remnant Gemini, or multiple supernovae in subgroup B1 of the Pleiades moving group. The distance between the local arm and the next arm out, the Perseus arm, is about 6,500 light-years. The Sun, and thus the Solar System, is found in what scientists call the galactic habitable zone. The apex of the Sun's way, or the solar apex, is the direction that the Sun travels relative to other nearby stars. This motion is towards a point in the constellation Hercules, near the star Vega. Within 32.6 light-years of the Sun there are 315 known stars in 227 systems, as of 2000, including 163 single stars. It is estimated that a further 130 systems within this range have not yet been identified. Out to 81.5 light-years, there may be up to 7,500 stars, of which around 2,600 are known. The number of substellar objects in that volume are expected to be comparable to the number of stars. Of the 15 nearest stellar systems within 17 light-years from Earth, the closest being the red dwarf Proxima Centauri at approximately 4.2 light-years, the Sun ranks fourth in mass. Orbit in Milky Way. The Sun orbits the center of the Milky Way, and it is presently moving in the direction of the constellation of Cygnus. A simple model of the motion of a star in the galaxy gives the galactic coordinates x, y, and z as backslash display style xt equals x0 plus backslash frac u0 backslash kappa backslash sin backslash kappa t plus backslash frac v0 to b1 backslash cos backslash kappa t backslash display style yt equals y0 plus 2a backslash left x0 plus backslash frac v0 to b backslash right t backslash frac backslash omega 0 b backslash kappa v0 backslash sin backslash kappa t plus backslash frac 2 backslash omega 0 backslash kappa 2 u0 1 backslash cos backslash kappa t backslash display style zt equals backslash frac w0 backslash nu backslash sin backslash nu t plus z0 backslash cos backslash nu t, where u, v, and w are the respective velocities with respect to the local standard of rest. A and B are the Oort constants. Backslash display style backslash omega 0 equals AB is the angular velocity of galactic rotation for the local standard of rest. Backslash display style backslash kappa equals backslash sqrt, 4 backslash omega 0 B is the epicyclic frequency, and nu is the vertical oscillation frequency. For the Sun, the present values of U, V, and W are estimated as backslash display style u0 v0 w0 equals 10.00, 5.25, 7.17 km per second, and estimates for the other constants are A equals 15.5 km per second /kpc, B equals minus 12.2 km per second /kpc, kappa equals 37 km per second /kpc, and nu equals 74 km per second /kpc. We take x0 and y0 to be 0 and z0 is estimated to be 17 parsecs. This model implies that the Sun circulates around a point that is itself going around the galaxy. The period of the Sun's circulation around the point is backslash display style 2 backslash by slash backslash kappa, which, using the equivalence that a parsec equals 1 km per second times 0.978 million years, comes to 166 million years, shorter than the time it takes for the point to go around the galaxy. In the x, y coordinates, the Sun describes an ellipse around the point, whose length in the y direction is backslash display style 2 backslash times backslash sqrt backslash left backslash frac 2 backslash omega 0 backslash kappa 2 u0 backslash right 2 plus backslash left backslash frac backslash omega 0 b backslash kappa v0 backslash right 2 equals 1035 backslash text parsec, and whose width in the x direction is backslash display style 2 backslash times backslash sqrt backslash left backslash frac u0 backslash kappa backslash right 2 plus backslash left backslash frac v0 to b backslash right 2 equals 691 backslash text parsec. The ratio of length to width of this ellipse, the same for all stars in our neighborhood, is backslash display style 2 backslash omega slash backslash kappa backslash approx 1.50. The moving point is presently at backslash display style x equals backslash frac v0 to b equals 215 backslash text parsec. Backslash display style y equals backslash frac 2 backslash omega 0 backslash kappa 2 u0 equals 405 backslash text parsec. The oscillation in the z direction takes the Sun backslash display style backslash sqrt backslash left backslash frac w0 backslash nu backslash right 2 plus z0 2 equals 98 backslash text parsec. Above the galactic plane and the same distance below it, with a period of backslash display style 2 backslash by slash backslash nu, or 83 million years, approximately 2.7 times per orbit. Although backslash display style 2 backslash by slash backslash omega 0 is 222 million years, the value of backslash display style backslash omega at the point around which the Sun circulates is display style omega approx omega 0 frac 2 ar sub 0 delta x approx 26.1 text kilometer per second kpc. CO or constants, corresponding to 235 million years, and this is the time that the point takes to go once around the galaxy. Other stars with the same value of display style x plus v/2b have take the same amount of time to go around the galaxy as the Sun and thus remain in the same general vicinity as the Sun. The Sun's orbit around the Milky Way is perturbed due to the non-uniform mass distribution in Milky Way, such as the tenon between the galactic spiral arms. It has been argued that the Sun's passage through the higher density spiral arms often coincides with mass extinctions on Earth, perhaps due to increased impact events. It takes the solar system about 225 to 250 million years to complete one orbit through the Milky Way, a galactic year, so it is thought to have completed 20 to 25 orbits during the lifetime of the Sun. The orbital speed of the solar system about the center of the Milky Way is approximately 251 kilometers per second, 156 miles per second. At this speed, it takes around 1,190 years for the solar system to travel a distance of 1 light year, or 7 days to travel 1 astronomical unit. The Milky Way is moving with respect to the cosmic microwave background radiation, CMB, in the direction of the constellation Hydra with a speed of 550 km per second, and the Sun's resultant velocity with respect to the CMB is about 370 km per second in the direction of crater Leo. Theoretical problems. Coronal heating problem. The temperature of the photosphere is approximately 6,000 K, whereas the temperature of the corona reaches 1 million to 2 million K. The high temperature of the corona shows that it is heated by something other than direct heat conduction from the photosphere. It is thought that the energy necessary to heat the corona is provided by turbulent motion in the convection zone below the photosphere, and two main mechanisms have been proposed to explain coronal heating. The first is wave heating, in which sound, gravitational or magnetohydrodynamic waves are produced by turbulence in the convection zone. These waves travel upward and dissipate in the corona, depositing their energy in the ambient matter in the form of heat. The other is magnetic heating, in which magnetic energy is continuously built up by photospheric motion and released through magnetic reconnection in the form of large solar flares and myriad similar but smaller events, nanoflares. Currently, it is unclear whether waves are an efficient heating mechanism. All waves except Alfvén waves have been found to dissipate or refract before reaching the corona. In addition, Alfvén waves do not easily dissipate in the corona. Current research focus has therefore shifted towards flare heating mechanisms. Faint young Sun problem. Theoretical models of the Sun's development suggest that 3.8 to 2.5 billion years ago, during the Archean, the Sun was only about 75% as bright as it is today. Such a weak star would not have been able to sustain liquid water on Earth's surface, and thus life should not have been able to develop. However, the geological record demonstrates that Earth has remained at a fairly constant temperature throughout its history, and that the young Earth was somewhat warmer than it is today. One theory among scientists is that the atmosphere of the young Earth contained much larger quantities of greenhouse gases, such as carbon dioxide, methane, than are present today, which trapped enough heat to compensate for the smaller amount of solar energy reaching it. However, examination of Archean sediments appears inconsistent with the hypothesis of high greenhouse concentrations. Instead, the moderate temperature range may be explained by a lower surface albedo brought about by less continental area and the lack of biologically induced cloud condensation nuclei. This would have led to increased absorption of solar energy, thereby compensating for the lower solar output. Observational history. The enormous effect of the Sun on Earth has been recognized since prehistoric times, and the Sun has been regarded by some cultures as a deity. Early understanding. The Sun has been an object of veneration in many cultures throughout human history. Humanity's most fundamental understanding of the Sun is as the luminous disk in the sky, whose presence above the horizon creates day and whose absence causes night. In many prehistoric and ancient cultures, the sun was thought to be a solar deity or other supernatural entity. Worship of the sun was central to civilizations such as the ancient Egyptians, the Inca of South America, and the Aztecs of what is now Mexico. In religions such as Hinduism, the sun is still considered a god. Many ancient monuments were constructed with solar phenomena in mind. For example, stone megaliths accurately mark the summer or winter solstice. Some of the most prominent megaliths are located in Nabta Playa, Egypt, Nijdra, Malta, and at Stonehenge, England. Newgrange, a prehistoric human-built mound in Ireland, was designed to detect the winter solstice. The Pyramid of El Castillo at Chichen Itza in Mexico is designed to cast shadows in the shape of serpents climbing the pyramid at the vernal and autumnal equinoxes. The Egyptians portrayed the god Ra as being carried across the sky in a solar bark, accompanied by lesser gods, and to the Greeks, he was Helios, carried by a chariot drawn by fiery horses. From the reign of Elagabalus in the late Roman Empire, the sun's birthday was a holiday celebrated as Sol Invictus, literally unconquered sun, soon after the winter solstice, which may have been an antecedent to Christmas. Regarding the fixed stars, the sun appears from Earth to revolve once a year along the ecliptic through the zodiac, and so Greek astronomers categorized it as one of the 7 planets. Greek planetes, wanderer. The naming of the days of the weeks after the 7 planets dates to the Roman era. Development of scientific understanding. In the early 1st millennium BC, Babylonian astronomers observed that the sun's motion along the ecliptic is not uniform, though they did not know why. It is today known that this is due to the movement of Earth in an elliptic orbit around the sun, with Earth moving faster when it is nearer to the sun at perihelion and moving slower when it is farther away at aphelion. One of the first people to offer a scientific or philosophical explanation for the sun was the Greek philosopher Anaxagoras. He reasoned that it was not the chariot of Helios, but instead a giant flaming ball of metal even larger than the land of the Peloponnesus, and that the moon reflected the light of the sun. For teaching this heresy, he was imprisoned by the authorities and sentenced to death, though he was later released through the intervention of Pericles. Eratosthenes estimated the distance between Earth and the Sun in the 3rd century BC as of stadia myriads 480,000, the translation of which is ambiguous, implying either 4,080,000 stadia, 755,000 kilometers, or 804 million stadia, 148 to 153 million kilometers, or 0.99 to 1.02 astronomical units. The latter value is correct to within a few percent. In the 1st century AD, Ptolemy estimated the distance as 1,210 times the radius of Earth, approximately 7.71 million kilometers, 0.0515 astronomical units.